All right, I'm working through the first problem in dynamics review for this unit. In the problem, you're described these block A and block B on the tabletop with the pulley. There is no friction involved, right? Which means that the block A is free to move along the horizontal tabletop without any issues whatsoever, right? We're going to be answering these questions about how the system would change based on whether block A or block B is much more massive than the other. But I do want to kind of illustrate something really quickly about these blocks, right? That if we looked at these two blocks, the net force is really just due to the mass of block B pulling down towards the ground, right? And there is tension in this rope, but since there's equal tension in both directions, they just cancel out. So really, that MBG is the only force that's going to be affecting the motion of the object. So, suppose the mass of block A is much greater than the mass of block B. We're supposed to estimate the magnitude of acceleration of the blocks after we release it. We don't want to use equations or anything like that, right? Think of it this way, right? If block A was just a very massive block, right? And block B was a very tiny block. And it would exert a small force on block A, right? But since there's no friction, there is no resistance to motion. So it would still want to move. It would just move at a very slow rate. You can also take this basically to be as if block B didn't exist. Obviously, block A wouldn't move at all. But because it does exist, it does move just a very small amount. So the acceleration would be close to 0. Since the net force is due to the weight of B, but system mass is very large compared to that. Right? We'll get to the equation later, but basically, because there's so much mass in the system and so little of that mass is actually what's causing the motion, the acceleration will be very small, basically close to 0. In the second one, block A is much less than block B. So block B is the massive one in this case, right? So now we have a situation where block B here is the very large mass, and then block A is just a tiny little mass that sits on the surface there, right? And then there's no friction again, so block B would just kind of free fall, right? Block A is basically offering very little resistance to the net force, or very little inertia, I guess. And so the acceleration would be close to g, or 10 meters per second squared. The reason is that when it's in free fall, right, when the object's falling, it can only fall towards the ground at that rate. So if block A isn't there, this is just a thing that's falling straight down. No matter how much mass it has, it's still going to fall at this rate. Since block B is basically in free fall. Now we want to draw the free body diagram for this situation, right? In this case now, block A and block B have, closer, more similar masses, but not the same not necessarily the same masses, right? So they don't really care about the length of these vectors. So this is mass of A times G, that's the force of gravity. Then there's a force upwards, which we'll call the normal force. And then there's a force to the right, which is the tension on the system, or on block A, right? Block B is a force downwards, which is its mass times G. And then there's a force upwards, which is the force of tension from the string, right? We want to derive an equation for the acceleration of this block, of these blocks, in terms of ma, mb, and physical constants as appropriate. Kind of going back to our original diagram all the way up here, right? That's not what I wanted to do. This diagram here, these are forces in the x direction, right? There's forces in the y direction, but they're not relevant. These are the only forces that are going to matter here, right? So our equation is going to be that the net force in the x direction is going to be the force of tension to the right minus the force of tension to the left plus the mass of B times G. And then this is going to equal to the mass of the system, right? Which in this case is the mass of A plus the mass of B times the acceleration of that system, okay? Again, we're taking sort of for block A, this is the x direction, and then for block B, downwards is the x direction, right? So we're sort of rotating block B 90 degrees so that MB, and FT are the x forces, okay? And so then we take this equation that we have here and we solve. FT's cancel out, right? FT minus FT would be 0. So I have MBG is equal to MA plus MB times A. And then I would divide both sides by that mass. Okay? And so the acceleration is just mb times g over the mass of A plus B. Right? Remember, mbg, this is our net force, really. And then this is the mass of the system. All right. Moving on to D, consider the scenario from part A2, which is the one where block A is much less than block B. Does our expression or equation that we just solved for, right, this one up here, does it agree with the reasoning, right? Well, yes it does, because we said that the acceleration would be close to G, right? And basically, as the mass of B becomes much greater than mass of A, right, the total mass becomes approximately just the mass of B, right? MA is so small that it doesn't really change the mass very much of the system, and so the total mass is just MB, right? So in our equation, we have MBG over MA plus MB. So what we're saying here is that basically MA is so small, it's almost like 0 in this equation, right? And so since this is equal to our acceleration, what ends up happening is that MA doesn't really matter. It basically goes to 0, right? So we just have MBG over MB, okay, equal to our acceleration. The masses cancel out, and so A just becomes G. Total mass becomes MB, and so the acceleration is basically G. And I would include either the equation there, or a more clear explanation of the math that I showed you there. Okay.